Hi kids, welcome back to the second set of video lectures for this course. This unit is on energy, conservation of energy, momentum, and conservation of momentum. And the first video in the series is on energy types, transfers, and transformations. Our essential question is, what is energy and how does it move around in a system? Energy is going to be a new variable for us in this unit. We're going to use the letter E to represent energy. And the units for all energy values are going to be the joule, or capital J. A joule is actually made up of a combination of the other units. I don't want to go into those details right now, but would be happy to help you individually if you're curious about that. Our definition for energy is the potential to make something useful happen, or the ability to do work. I don't think it's a really concrete definition, but most of you guys have a sense of what energy is because you use that term in your lives so often, and it's pretty similar to the way you use energy. If you have a lot of energy, you've got a lot of potential to make things happen. You feel strong and powerful, and you have lots of ability to do work. So that's basically how we define energy. There are two categories of energy, which you may have learned about in a prior science class. Those categories are kinetic and potential. I think we're going to be a little clearer on exactly all the different types of kinetic and potential energies than you've probably learned before. But we are going to be using those words as far as categories of energy. So the word kinetic energy specifically means that an object or a part of an object is moving. So there's actually lots of different types of kinetic energy. You probably learned about just the first type that we're going to talk about, which is, we're going to call it EM for motion energy. So when a whole object is just rolling down a hill or driving down a street or just running, that object has the potential to do work. It could run into something and make something useful happen. So we're going to call that kind of energy for a moving object motion energy. And we're going to label it E with a little m, so we can be clear about exactly what's going on. Some examples of objects that have motion energy. A turtle would have a small amount of motion energy, and a race car would have a lot. There is an equation for motion energy. We're not going to be using it, but you can probably guess that the smaller the object is and the slower the object is, the less motion energy it has. And the larger and faster the object is, the more motion energy it has. So while we're not going to be using the equations, it is important for you guys to have a sense about what types of objects are going to have a lot or a little of each of these types of energies. Another kind of kinetic energy is rotation energy. So objects can be rotating even if they're not moving the whole object. And so it's a different kind of energy, ER. Some examples of objects with rotation energy. A bike tire, when it's spinning, has rotation energy. And not a lot of rotation energy, but something bigger like a planet that's rotating a lot faster than the bike tire would have a lot more rotation energy. So again, the size and the quickness with which it rotates are going to be factors that determine how much rotation energy an object has. A third kind of kinetic energy is called thermal energy, and I'm sure many of you know that heat is energy, but you may not know that it's a kinetic energy. And the reason it's a kinetic energy is because thermal energy is actually caused by the movement of tiny little atoms or molecules inside an object. So if you could zoom in with a microscope, you'd see that every atom is actually jiggling and moving around all the time inside every solid object. And that movement of the atoms inside an object is known as the thermal energy. Everything has thermal energy, even if it's cold. So something like ice has thermal energy. Of course, it doesn't have a lot of thermal energy because it's cold, so those atoms are still jiggling and moving. They're just not jiggling and moving very quickly. The hotter the object gets, so lava, for example, the more thermal energy it has because the atoms inside of it are moving much more rapidly. Another kind of kinetic energy, light energy, or EL. Light energy, of course, moves from place to place. When you turn on a light, the little photons of light move through space, and that's why they're kinetic energy. An object that has not very much light energy would be like a flashlight, a dim flashlight, and the brighter the object is, the more light energy it's going to contain. So lasers, for example, are going to have a lot of light energy. The last kind of kinetic energy we're going to talk about is EW, which is wave energy. There's lots of types of waves. This is going to be a whole unit for us later on in the year. Sound, light is actually a kind of wave also, water waves, slinky waves, heat waves. There's lots of different kinds of waves. So examples of objects that have a little bit of wave energy: a whisper, so a very quiet sound, is not going to have very much wave energy. Of course, a tsunami, which is a massive ocean wave, would contain a lot more wave energy. And obviously waves move through space, so that explains why they are going to be kinetic energies as well. Potential energy, on the other hand, is energy that an object has based on its shape or position, which is storing up energy. So we're not moving this time, it's just storing up energy based on the shape or position. The kind of potential energy you're probably familiar with is gravitational energy, gravitational potential energy, or EG. So obviously when you lift up an object high, it's got the potential to do something. If you drop it, it could really hurt, could hammer in a nail, do something useful like that. So when you lift an object up high, you give it gravitational energy. Some examples of objects with gravitational energy: snow, which has a little tiny bit of it, and a space shuttle, which has a lot. Obviously, the more mass the object has, the more gravitational energy it's going to have, and also the higher you lift it. Another kind of potential energy, EE, which is electrical energy, which is energy stored up by electrons and protons and their relative position compared to each other. So an object with not a lot of electrical energy would be an electron. If you don't know what that is, we'll be covering that in a future unit, but it's a really tiny little piece of an atom. And of course, you've all seen those high voltage power lines. Those are going to have a lot more electrical energy. They have a lot more atoms, and those atoms are squished much closer to each other, which gives them a lot of electrical energy. A third type of potential energy is spring or elastic energy. We're going to call that ES. And a rubber band has some spring energy, and but just a little bit. Car shocks, of course, have a lot more spring energy. They have more energy because it's harder to compress them. That means they exert a lot more force when they are either stretched out or compressed compared to the rubber band. A fourth kind of potential energy is chemical energy. This is a really common, important one because chemical energy is the energy that we use in our bodies all the time. We take in energy in food, like peanuts, and our bodies store it in a different kind of chemical energy. The fat in our body is actually another kind of chemical energy as well. Peanuts, of course, don't have a lot, which is why we need to eat a lot of them. Something like a big, massive car battery is also storing chemical energy because it's got chemicals inside of it, and the reaction between them is storing some energy, but they store a lot more energy than a peanut would. The last kind of potential energy we're going to talk about is nuclear energy, or EN. This is energy that's stored up in the nucleus of an atom based on the positions of quarks and other subatomic particles, really tiny things inside the atom, but they can still store up a lot of energy. It turns out the bananas actually have some radioactivity in the potassium in bananas, so they would have some nuclear energy. Actually, everything has nuclear energy that has a nucleus, but a banana has more than some foods. And of course, a lot of nuclear energy in nuclear reactors, which are one of the ways that we generate electricity from nuclear energy to power all of our electrical grids. The big idea for this unit and last unit for that matter, but is conservation, and energy is another one of those things that is conserved in a closed system. So that being said, energy can transform from one type to another. So we mentioned all those kinds of energy in the last two slides. It can turn from one of those types to another type, and it won't be lost. It's just going to be now looking a little bit different than it did before. Energy could also transfer from one object to another. Maybe it changes types, maybe it doesn't. So you can have kinetic energy turn from one object, go into kinetic energy of another when they collide, for example. A car hits another car, and the motion energy of the first car goes into the second car. So if we have our closed system here, we can have energy changing all the time in that system, but the idea is that the total amount of energy in the system, the sum of all those kinds of energies, is going to be constant. So I mentioned two methods by which energy goes from one type to another. The first is called energy transformation. The word work in physics is the process by which energy is transforming from one type to another. So for example, a granny skydiving here, she starts off her dive with a whole lot of gravitational energy. She's really high above the planet and she's got some mass. And as she falls, some work happens and that gravitational energy is transformed into motion energy because she gets faster and faster as she falls. Another example, this is a little girl inside a Zorb, which is a big inflatable ball in some water, and she is turning her chemical energy, she's running as fast as she can, into primarily rotational energy in the Zorb because it's spinning around. So hamster in a wheel is pretty much the same idea there. Now, of course, in either of these cases, some other kinds of energy are generated as well, and often those are referred to as waste energy because they weren't really the intended kinds of energy when you went into that energy transformation. So we're not losing the energy, but sometimes you're turning energy into less useful types of energy than you were really intending to. The other way energy can move around a system is called energy transfer, and that's when energy moves from one object to another. If you think of anything in your life that has energy, you can actually transfer that energy back to the Big Bang. So you can have energy transfers all the way back to the original motion of the universe, which was the Big Bang. So for example, if you have a light on in your room right now, the motion energy from the Big Bang, when that tiny singularity exploded, it had a bunch of movement energy, and that turned into gravitational energy because the space dust got further apart and then it started trying to attract little other pieces of space dust. And when those pieces of space dust attracted, they eventually attracted enough that they turned into this really dense ball of chemicals called the sun. And so they had nuclear energy because then they got squished together so tight by their gravitational energy. Then over time, that nuclear energy explodes out of the sun and is transferred into light energy in the sunlight. And as that sunlight moves through the space, it comes to Earth's atmosphere where it starts heating up our sky and our ground, and that turns it into that sunlight into thermal energy. The thermal energy, of course, will cause water to evaporate from the oceans and go up into our atmosphere. Then that water falls as rain and goes into rivers where it has motion energy again, moving water, like for example the Columbia River water, which then in our Bonneville Dam gets transferred into electrical energy, which then goes through the wall socket and eventually gets transferred into the light energy in your bulb. So that's a whole bunch of energy transfers from one object to another to another to another. And almost any other, or well, not almost, every other kind of energy that you can think of could be tracked back to the Big Bang as well. So take a minute and see if you can summarize this series of slides. Ask yourself the question, what is energy and how does it move around in the system? See if you can answer those questions, which were our essential questions. I would also recommend that you take some time to fill out the graphic organizer in your notebook and work on the extension questions that will really help you be prepared for class. Thanks for listening.